Alright, so we're going to finish up chapter 22 with this pre-recorded lecture. As a quick recap of what we did last class, we started talking about Faraday's law in a more quantitative form, which says that in order to get the EMF induced within a loop of wire, you look at the change in flux that happens through that loop, the time it changes over, you multiply that by the number of loops you have. So if you have a coil of wire, you have many loops, you will multiply by that number, and then a negative, which accounts for the fact that that induced EMF acts to oppose the change in flux that occurs. In other words, to create an induced current whose own magnetic field opposes the change in flux that occurred within the loop. So we did a couple calculations with that, then looked at Lenz's law in more detail in order to figure out the direction of induced current flow. And the short of it is that nature does not like flux to change, and so will do what it can to oppose those changes, and that lets us figure out the direction of current flow. We saw an example of that with the ring launcher, and so I'm going to pull up that brief explanation of the ring launcher as a recap for that, and then it'll add a little bit of additional context as well. So this is the ring launcher we've already seen before. It is a solenoid, and that's just a long coil of wire. But when I press this switch, it's going to send a lot of current through the solenoid. So if I have something like a metal ring on there, when I press that switch, the current through the solenoid is going to generate a magnetic field that points upward. That's going to increase the flux through this ring. In order to oppose that, which Lenz's law says is what should happen, the field induced in the metal ring should point downward. And that magnetic field that is induced should be due to a current flowing according to the second right-hand rule. So in this case, if we want a field that points downward, our hand would go into the loop and our thumb would point around the loop like this. And so from a top-down view, that would be clockwise. That's going to make the ring act like a bar magnet as well as a solenoid, and they repel, making the ring jump. What if we had a little cut in the ring so that current can't flow all the way around? What do you think happens when we pulse it? Let's see. Not much of anything. And it's because if we have that cut, current cannot flow all the way around the ring, and so it can't create a magnetic field that opposes that change in flux. So the two don't repel. We're going to look at another one here to get some practice and see what the difference is when we have magnetic fields that are induced into versus out of a page. In this case, we have a magnetic field that is confined to a certain region. And in that region, it's into the page. We're going to slide a copper ring across that region. So you could imagine that this is us looking down at a tabletop, that we are generating a magnetic field pointing down into the table, and we're sliding a ring across the table. We want to know the direction of the induced current in the ring at each position shown. So in the first stage, the ring goes from having no flux through it because it is not in the magnetic field yet, to having flux present within at least part of the ring. That means that the flux increases within the ring, and although flux doesn't technically have a direction, I like to think of that as an increasing flux into the page because more field lines are poking down into the page for the ring as the ring enters the magnetic field. Second step in Lenz's law is to consider what needs to be done to oppose that change in flux. So if we have more flux into the page, the induced magnetic field should create a flux out of the page to oppose it. So the induced field within the ring must be out of the page to oppose the change in flux within it. And we represent out of the page with dots instead of crosses. So we should have a field within this ring that is now pointing out of the page as it's entering the magnetic field region. In order for that to happen, the current flowing around the ring must be able to create a out of the page magnetic field. And so the second right-hand rule says our fingers should come up out of the page, or in other words, be pointing at us as we're looking at this. The only way we can grab the ring for that to happen is if our thumb is holding on to it like this. So if these are our fingers sticking up through the loop, our thumb is grabbing on like that, and so That is why the current flows counterclockwise in this picture. It's not a very good hand, but hopefully it helps to see this a little better. So, by the second right-hand rule, the induced current must be counterclockwise in order for the induced magnetic field, the one represented by the dots here, to be out of the page. So that is the direction of induced current flow in the ring as it enters this field. Once it is in the field, it's not going to have any increase or decrease in flux happening. So if we think about once it's fully in the field to over here, there will be no change in flux, and so no current induced. We're seeing no change in flux. Because there's no change in flux, there's nothing to oppose, so there is no induced magnetic field. And if there is no induced magnetic field, there is no induced current creating it. But now we look at as the ring is exiting this magnetic field region again. In that case, we're going to see the flux decrease. And in this case, we have less flux, we could say, into the ring as it leaves the magnetic field. Lenz's law says that the induced magnetic field should oppose that change. In order for it to do that, it's saying, hey, I don't want the amount of flux through the ring to drop like that, so I'm going to try and bump it back up, and the only way that can happen is if the induced field is also pointing into the page, compensating for the amount of field lines that are not there anymore from the main magnetic field. So it must be into the page this time to oppose the flux change. And again, by the right-hand rule, the current around the ring has to flow a certain way to create that induced magnetic field. In this case, if we think about that our fingers should dip down into the loop, and so our thumb should point the other way, and that's indicating the direction of current flow. So in this case, the induced current must be clockwise for this induced magnetic field to be into the page. So, as the ring enters the field, the induced current is counterclockwise. As it leaves the field, the induced current is clockwise. And another thing worth mentioning is that Lenz's law doesn't say that the induced field always points the opposite direction of the original field. It just says that the induced field opposes any change in flux that we see from the original field. So, right here, as the ring was leaving, the magnetic field that's induced is pointing in the same direction as the original field because it's trying to replace flux that was lost as the ring is leaving that region. Okay, so we've been talking for a while about induction and how it can cause current to flow through a wire, but in order for current to flow, you need some energy source. How is that coming to be? So we're going to look at another type of induction. It's similar to the example we just considered. So as the loop exits the field, the flux into the page will decrease. So the induced magnetic field, created by the induced current flowing around the loop, must point into the page to oppose this change in flux, this drop. So our induced field will be more like this. That is again going to indicate current flowing clockwise. Like with any other circuit where current is flowing, that can be used to deliver energy to a resistor, or in this case a light bulb, and that energy can be dissipated as light and heat. We got to figure out where that energy is initially coming from. We're going to do a little bit of math, and the result will give us a hint at what's going on. So let's first try and derive an expression for that induced current. In order to do that, we need to apply Faraday's law, and in order to do that, we need to find the flux through the loop at any time. So flux is magnetic field strength times the cosine of the angle between that field and the normal to the loop. In this case, the loop is aligned with the magnetic field, or its normal is pointing in the same direction as the magnetic field. So we can say that angle is 0, and then times the area of the loop that is sitting within the field. Not necessarily the entire area, but just what is within the magnetic field. So cosine 0 is 1. We don't need to worry about that bit, but we can write that area as the length of the loop, L, times however much of the loop is currently within the field, X. So this number, X, can vary as we pull the loop out, and it will get smaller in that case. To find the size of the EMF that is induced, we'll ignore the signs here, just worry about the size of it. So we'll leave that negative out of Faraday's law. The number of loops is just 1. So we can write Faraday's law as change in flux over time, or change in the quantity from the previous line, BLX, over time. And if we think about what's changing here, the magnetic field strength isn't. We're dealing with a uniform field. The length of the wire is not changing. It is X, how much of the loop is within the field that's changing. So I'll factor everything else but that out. But you may recognize this as the speed of the loop as it's being moved out of this field. This is just BL times that speed. So the current comes from knowing the resistance of everything in our circuit. That will primarily be the resistance of the light bulb in this case. It acts like a resistor. And so from the relationship between current, voltage, and resistance, we can write that as the induced EMF over resistance, or substituting in from above, we get that right there. And so the power used by the bulb, which is the rate at which energy is delivered to it, we can write as current squared times resistance, just like usual. I'll put this in for the induced current, and after some simplification, I will get B squared, L squared, V squared over R. To see the significance of this, we can think about each term. This is saying that because the power dissipated by the bulb is related to the brightness of the bulb, if we have a stronger magnetic field, we have a larger loop, or we pull the loop faster, we will get more power dissipated, the bulb will glow brighter. If the resistance is lower, that will also make the bulb glow brighter. The faster you pull, or the bigger the loop, or a couple other things, but I'll focus on those, the more power dissipated, and so the brighter the bulb. So, we finally come to the question of where that energy is coming from. Well, this says that the faster we pull, the more energy is being delivered to the circuit. So the energy is coming from us. In this case, from the hand pulling. On the first day of this chapter, I would repeatedly put a loop into and out of a magnetic field. The faster I pulled or pushed the loop into the field, the more current would flow through it. So the energy is coming from my body and being converted into electrical and eventually thermal energy in the resistor through magnetic means. It's pretty strange. How is it doing that? Well, we've got a little bit more going on than our figure lets on right now. The first bit is, thinking back to chapter 21, because we have a current flowing this way through this magnetic field, currents within magnetic fields feel magnetic forces. By the first right-hand rule, our thumb would point that way, our fingers would point into the page, which I don't think is even worth trying to get right for me, but into the page, not to the left. But then as a result, our palm would point leftward in this picture. That bit of the wire would feel a magnetic force to the left. So do these pieces, but if the current is the same on either side, and it will be since they are in series with each other, these two forces will cancel each other out. So the only one worth focusing on is this one. It's resisting our pull, trying to remove the loop. And so, as a result, the energy we're putting in is not all being converted into kinetic energy to speed the loop up. Some of it is being used in the circuit as electrical energy. We're not violating conservation of energy, we're just not able to speed the loop up as much as we could if the magnetic field weren't there, because some of the energy is going into that induced current. So in summary, the loop feels a magnetic force opposing our pull. In order to keep the loop moving, we have to do work, and some of that work is transferring energy not to the motion of the loop, but to this induced current. In this perfect situation of moving at constant velocities so that none of our energy is going to speeding up the loop, all of it is going to electrical energy, and so going to the light bulb. The rate at which we're doing work equals the rate at which energy is being used by the bulb. So our mechanical energy is what becomes the electrical energy that pushes charge through this circuit into the light bulb to dissipate it as thermal energy. This is still conservation of energy at work. And the thing mediating this is the magnetic field, the green one. It's what allows that type of conversion to happen. It's not doing work directly itself, but it is letting us convert our energy to electrical energy. This kind of induction, by the way, is sometimes called motional EMF, and you'll hear that term pretty often still, but nowadays it's not considered any different from any other type of induced EMF and resulting induced current. We'll just sometimes use this expression because we already figured it out for a moving wire, but it still stems from Faraday's law. And so we're going to see that here with generators. They are a little bit more of an efficient way to convert mechanical energy to electrical. So they're a fancier version of this experiment here. And this is what powers our whole electrical grid. This is what is producing the electrical energy that eventually reaches our house. Very large electric generators. How they work is pretty much the opposite of motors, so this picture should look a little familiar. In this case, we rotate the loop ourselves, and that will induce a current within the loop. To figure out the direction current flows, we again use Lenz's law. So if we are rotating this loop as shown, doing that is going to make more of the loop face the magnetic field or be aligned with it. That's going to increase the flux through the loop. In particular, increase the amount of flux pointing through the loop to the right. To oppose that change, as Lenz's law says should happen, we should have an induced magnetic field that points to the left. And the only way we can have that kind of induced magnetic field is if we think about the second right-hand rule. If our field is to point to the left, our fingers should dip into it that way. And that would mean our thumb is holding on like that. In other words, current flows this way around the loop. As the loop continues turning, eventually it will see a decrease in the flux through it, and that will make current flow the other way. And that is why the direction of current flow alternates from a generator that is alternating current. All right, so we figured out the direction of current flow. Let's figure out the induced EMF that causes it, because that is what is going out to the electrical grid. The voltage that reaches your house is in some indirect way stemming from a generator like this, just a much fancier one. We saw in the previous section that you can induce an EMF through motion, and the size of it is the strength of the field times the length of the wire in the field times the speed of the wire. We got to be a little bit careful here. I'm going to write that BLV perpendicular. And the reason for that is, if we think about at any instant, this wire is rotating in a circle. So if we had a top-down view, we'd see pretty much just this, and then this is the part that connects up to the light bulb. That is spinning around and around and around in a circle. And at any instant, the velocity is tangent to that circle. On our original picture, that's going to look something like this, and the other side going exactly the opposite direction. Let's split that into components that are in the direction of the magnetic field and perpendicular to the direction of the magnetic field. And we'll call this angle theta. It will again be between the normal to this loop and the magnetic field direction. In that case, this over here is V sine theta. This is V cosine theta. If we're moving a loop in the direction of a magnetic field, we are not going to see induction happen because it's not going to change the flux through the loop. It's only moving it perpendicular to that field that would change the flux through it. And so this is what I'm talking about when I say the perpendicular component of V. It's the part that actually leads to an induced EMF. So I'll write that over here, BLV sine theta. And that's going to be the EMF induced in either wire. To get the EMF induced in both, you will add that together, so you will get twice that for the overall EMF induced in the loop. If we have N loops, or a coil of wire, it will be N times whatever we found for one loop. And so, like we said, it's twice what we found for a single wire. I'll just kind of regroup things. 2N V sine theta L B, where L is the length of either wire, B is the strength of the field, N is the number of loops, V is the speed at which the loop is rotating in meters per second, theta is the angle between the normal to the loop and the magnetic field, and that is it. So it's a lot, but we'll see where this is going in just a second. So if we're rotating this loop, we think back to physics 1 to talk about rotational speed, we use omega. That's saying what angle something is rotating through per second. It is related to the linear speed, the number of meters per second, by V equals R omega. What that's saying is, if I'm out here on the edge of the loop, I'm covering a certain circumference each second, or a certain arc length. I'm going around this circle. That's a number of meters per second. But I could also talk about what angle I'm rotating through per second. If it's one complete revolution each second, that would be 360 degrees per second, or 2 pi radians per second is another way of putting it. Or I could say 2 pi times the radius, and that would give me the number of meters per second. So that's how I get from angular speed to linear or tangential speed, is through the radius. Another thing we can talk about from Physics 1 is that angular speed can be written as the angle you're moving through per time. This would be the average value, but if it's constant, it's also the instantaneous. So we solve that for theta, right? Angular speed times time. I'm going to put those in for v and theta. And in this case, I need to think about what my radius is. It's going to be half the width of the loop. So my axis is right here. I'll call the width of the loop w. So not omega, but w. And so the radius is half that, or w over 2. So that's what should go here for my radius at which each vertical wire is rotating. W over 2 times omega. If I carry what I had up above down here, I substitute in w over 2 omega for the linear speed, sine omega t for the angle theta, lb. Those 2's will cancel. I've got w times l in this expression. That's going to be the area of my loop. It's width times length. And so I can group those together as area. And that will leave me with the expression that the induced EMF in this generator coil is the number of loops times the area of each loop times the magnetic field strength times the angular speed times the sine of omega t. This is still a little bit intimidating, but the idea is that if you have more loops, you have bigger loops, you have a stronger field, or you rotate the loop faster, all of those will give you a larger EMF induced. And you can think of that indirectly as a brighter bulb. So these are all going to be properties of the loop or the field we put it in, but this is something we could directly control, is how fast we rotate it. So that's a mechanical property. How much you put in determines how much electrical energy you get out. So a generator can be thought of as a converter from mechanical to electrical energy. If we think back to a motor, we found that the torque on a coil in a motor is NAB, the same stuff as here, but multiplied by the current through each loop in that motor times the sine of omega t. So here, again, this is stuff about the field and the loop we choose. We can control the current through it. That is an electrical thing we can control, and convert that to a torque, a rotation. So we get something mechanical out. This is why we say that generators and motors are the inverse of each other, and in many cases you can turn a motor into a generator and vice versa. So we've got a quick example here, and then I'm going to pull up a video showing this idea of a generator. We've got the coil rotating at a frequency of 60 Hertz, develops a peak EMF of 170 volts. We're given the area of the coil and the number of turns. We want to find the magnitude of the magnetic field the coil rotates in, so that's B. Well, our expression tells us the EMF at any time, and we see that it's going to vary because of this sine omega t term. Remember, sine oscillates back and forth. So one thing that's worth noticing is that it says peak EMF. What's the largest this can be? At most, sine can be 1. It goes between -1 and 1. So we'll say this is 1 at most. And so best case scenario, the induced EMF we're getting out is NAB. Whoops, I forgot my omega right here. NAB omega. And we're told that that is 170 volts. If we solve for the magnetic field, it is that peak EMF over the number of loops times the area of each loop times the rate of rotation, the angular speed. So we're almost done, but we notice we're given frequency F, not omega. What's the difference between the two? Well, again, that's a physics 1 thing. The relationship between the two is this. And it's because this is telling you the angle per second, but this is telling you the number of cycles per second. So if you're going through one cycle, one complete rotation of the loop each second, you're covering an angle of 2 pi. If you're going through 2 complete rotations each second, it's twice that, or 4 pi. So we should write this as that peak EMF over number of loops, area of each loop, 2 pi times this frequency, where it's measured in hertz, or 1/seconds is what a hertz is. So 170 over 500 turns, no units on that. Area of each loop, running out of space here as usual. Still got to multiply by 2 pi, and then that frequency of 60 hertz. If we calculate all of that, we get 0.3 Tesla. So I want to show you that you can create a generator with a magnet and a loop of wire, and that the faster you rotate it, the larger this number omega is, the more induced EMF you will get. So the larger the induced current, so the larger the power generated. And if we have a light bulb attached to the generator, that's going to make the light bulb glow brighter. So let me pull that up. Okay, so this is a little hand crank generator, and if I turn the crank on it, it is going to rotate a coil inside of this metal enclosure. There's also a magnet in there, and so as the coil rotates in that magnetic field, that is going to induce a current that will flow through the wires and light up this little bulb right here. So the mechanical energy I'm going to be producing with my hand is being converted to electrical energy that flows to the bulb through the use of a magnetic field. It's the thing that hands off the mechanical to electrical energy, and then it's finally dissipated as thermal energy and light through the bulb. So I'm going to start with a slow spin. If I spin faster, we're going to see more current flow because there's a larger induced EMF when we have faster motion. And so the bulb lights up brighter. Similar devices are used in hand crank radios for emergency situations. You can also bring a little hand crank generator when you go camping in case your phone dies, and you can sit there turning the crank for a while. It will take a while to recharge your phone that way, but it is possible. And so you can see really directly how we're converting mechanical energy into electrical energy with a generator. All right, so the last thing that we'll talk about in this chapter is mutual and self-inductance. Before, we've seen that I can induce an EMF by pulling that coil or loop out of a field. I can change the area of the loop or the orientation of it, or make the field stronger. We talk about mutual and self-induction when we're talking about changing the current through one loop or coil in order to generate or induce an EMF through a second loop or coil. So that's all mutual induction is we know that when I create a current in one coil, it will create its own magnetic field. That will change the flux through a second coil if we place it nearby. That's why we call it a secondary coil. And that change in flux will induce an EMF within it, and that will cause current to flow within it. So you can have this wireless transfer of energy. Wireless in the sense of there's a gap between the two. Of course, there's wires on each. So we talk about how well the two coils are placed relative to each other in terms of mutual inductance. Okay, so if we think about what we're able to control here, this is a generator. I'm going to replace it with a battery just to make this a little bit more concrete, and say the battery has this polarity. That's going to send current down through here. I'll call that I1, and it will eventually return. That's something I can choose by choosing the battery I put in. And so that might be kind of a control parameter I think about as an engineer or scientist that I can choose the value of. But what that's going to do is generate a magnetic field in the primary coil. Because of the direction the current is flowing, I can use my second right-hand rule. My thumb would point down, and the rest of my fingers would go through the loop to the right. I wish I could draw that a little bit more clearly, but here we are. So the second right-hand rule says that's going to generate this magnetic field to the right. And we can see now in the secondary coil, that's going to lead to a flux through it a certain number of field lines passing through the second coil. If we think about the flux through any one of those loops in the second coil, let's call that phi2, flux 2. And so the total flux through the secondary coil will be the number of loops times the flux through any individual one. So I'm going to guess that the total flux, and I'll also use a subscript 2 for the number of loops in it, is directly proportional to the amount of current I have flowing through the first coil, through the primary coil. The proportionality factor I'm going to label N. So again, this just says the flux through the second coil is proportional to the current through the first. If I solve that for M, I get a way to measure it. What I do is I see how much flux I get through the second coil, and then compare it, divide by the amount of current I'm putting into the first coil. We call this stuff in the numerator the flux linkage because it's an indication of how well linked our two coils are. If I had put my secondary coil perpendicular like this, I'd get much less flux, and that would reflect in the flux linkage. And so we would have a lower mutual inductance. So the mutual inductance is the amount of flux you get through the secondary coil per unit, say per amp, of current through the first. So if this number is large, that's just saying that these two things are really well linked together. You're getting a lot of flux through the second coil, even if you put just a little bit of current in through the first. The units are, because the units of flux are Tesla square meters, and the units of current are amps, that is our SI unit. We give it a special name, one I like a lot, the Henry. And the reason we bother with this is it lets us write Faraday's law in a more practical way for this situation. If we think about the EMF induced in the second coil, where does that come from? Well, again, the second coil is suddenly going to see more flux through it due to the first coil's magnetic field, so B1. As a result of that increase in flux, it's going to try and oppose it, as Lenz's law says, by creating its own magnetic field. Call that B2. It is an induced magnetic field, but we'll call it B2. In order for the secondary coil to create a field that points that direction, the current through it has to flow according to the second right-hand rule. And so if we get a field pointing to the left, that's going to require the current through this loop to flow this way. And if that's the case, since current flows from positive to negative, that must be the polarity of our induced EMF in the second coil. And that can be measured by a voltmeter. So we would see a positive reading for this situation. Okay, so Faraday's law says the size of that induced EMF is the number of loops in our coil times the change in flux through them over the time that change occurs over, and the negative is just indicating Lenz's law that change in flux is going to lead to an EMF that opposes the change. So I recognize this right here as the mutual inductance times the current through the first coil. So I'm going to write it like that instead, equals negative M change in current through the first coil over time. And the reason I would do that is because then M is something that kind of is on the box, if you want to think of it that way. If you buy two coils that are set up in a specific arrangement, they could report that number M for you. And then you are just worried about controlling the current through the first to tell you how much EMF or voltage you're going to get through the second coil. That's a little bit more practical than every time trying to figure out the flux through the second yourself. And that is why the mutual inductance is a useful quantity. I'm going to pause before we go to self-inductance and show you a couple examples of mutual inductance. So I'm going to add the iron rod here, and that's just going to extend the magnetic field of the solenoid. And I'm going to put this coil on top. So this coil is just a coil of wire connected to a light bulb. When I put it on here and close the switch, something very similar to the ring's going to happen. We are going to have a sudden increase in flux through this coil. That's going to induce a current in it whose own magnetic field opposes that increase in flux. And that induced current is going to flow through the circuit, including the light bulb. So it'll light up. energy is being transferred from this coil to this one through a magnetic field. So that's mutual induction. It's when you have one coil and another near each other, and we would say that they are coupled or linked together in some way, in this case because this one's sitting on top of the other one, and that will induce an EMF in the secondary coil, and that will cause a current to flow through it, lighting up the light bulb. So that is actually exactly how wireless charging works. You just saw an example of it for the light bulb, but that light bulb could be replaced by your phone if your phone had a coil in it. And many new ones do, as does the wireless charger. And so through mutual induction, you can have a current induced in your phone coil to charge it up without it being directly connected to the charger coil. All right, another example that maybe is a little less practical, but I think is a lot more pretty, is something called the firefly lantern. All right, so this is one of my favorite examples of mutual induction. Here we have these two large rings that are going to act as our primary coil. And so when current flows one way around them, let's say this way around, then the second right-hand rule says that's going to produce an upward magnetic field. When current flows the other way around, the opposite direction, the second right-hand rule says a downward magnetic field should be produced. So by alternating the current, we're going to produce an alternating magnetic field that goes between up and down and up and down. That's going to change the amount of flux through these little coils on the inside, our fireflies, and they act as the secondary coils. So as the current alternates, that's going to change the flux through each little coil. That's going to induce an EMF in each one that causes current to flow around it. On each of the little coils is an LED, a little light that will light up as we get that induced EMF, and so the induced current flow through them. The reason they end up looking a little bit like fireflies when I turn it on is that how much flux is going through them is changing all the time. And so the rate of change of flux is also changing all the time. Not only because of this alternating current, but a little fan is going to blow these around in here. And so the area of each coil actually exposed to or aligned with the magnetic field is going to change all the time, as is the speed of each little firefly, and that's going to lead to a different induced EMF due to motion. So we have a changing magnetic field, a changing area, a changing orientation, and we have area changing due to a change in speed as the fireflies move around inside the tube. So pretty much every possible way we can see induction happens in here. So now I'm going to turn the lights off so we can see this a little bit better. I'll turn the fan on and we'll see the fireflies in action. So mutual induction is one that's a little bit easier to think about. The one that's trickier is self-induction. And it is also happening in this situation we looked at up above with the primary and secondary coil. But for it, we're going to zoom in and just look at the primary coil and what's happening in it. Again, we'll just think about one polarity for the generator. It's always alternating, but we'll just pretend it's just a DC situation, direct current, and so replace it with a battery. That's again going to make current flow, say I1, and as it flows through this loop, it is going to generate a magnetic field, like we said, according to the second right-hand rule. But here's the thing. If that is connected to a generator, the amount and direction of current flow is always changing. And so the size and direction of the magnetic field is changing. We have a changing magnetic field inside of the primary coil. That's going to lead to an induced magnetic field, as usual. And that induced magnetic field is going to oppose that change in flux that occurs, in this case, the increase that happens through the primary coil. So it should act opposite it. We get an induced field opposing our original field. In order for that to be the case, there has to be an induced current producing that field. And this is where it gets really confusing. That induced current, according to the second right-hand rule, should flow exactly the opposite direction of the original current. So this was the original I1. The induced current should flow the other way. So how is that possible that we have two currents flowing at once? Well, the answer is it's not. What's really happening is that the current flowing from here is going to be a little bit smaller than what we originally thought. It is as if there is some charge flowing the other way at the same time, but really what's happening is we've got a weaker, if you want to think of it as net current, flowing around the loop. And generally, the battery or generator is going to be stronger than, in this case, the induced EMF that is acting like a battery coming from this coil. Its polarity, by the way, would be this right here, the induced one. But you can see the situation. It looks like two batteries opposing each other, sort of fighting each other, and that's like replacing them with one effective battery that's a little bit smaller. That is why we sometimes call this self-induced EMF back EMF, because it's opposing the generator, and in doing so, making it as if the generator is a little bit weaker. We can quantify how much induction is happening within this primary coil through something similar to mutual inductance called self-inductance, or just inductance. So, similar idea. It's that because of this original current I1 flowing from the generator, that's going to lead to a flux through our coil, and through any one loop in that coil, that flux will be, we'll call it phi1. So the total flux through the entire coil will be N1 phi1. And so we're just saying, how much flux do we get per amount of current we put in? How much flux is there through the coil per unit of current we put into the coil? That's self-inductance. Amount of flux through coil per unit of current through it. The units will be the same as mutual inductance, Tesla square meters per amp, or henries. And the only difference between the two is this is all happening with one coil, both the current going through and the flux is talking about a single coil. Up here, we're talking about the current going through one primary coil, and then the flux resulting from that through the secondary, and how those are linked together. This is about like the self-linkage of the coil. And so we can again rewrite Faraday's law using that inductance. So Faraday's law is it's negative the number of loops, change in flux through any one loop over the time that flux change occurs over. But I can replace that using this definition of inductance as negative L change in current over time. And L, again, is something that if you bought one of these coils, it would have that number written on it. It's something that is special to that particular coil, and then you just control the current to change how much induced EMF you get, or back EMF. So, like we said, the direction of the EMF is such that it opposes that change in current. We could write that as, these things are called inductors, these coils of wire, when we use them this way. So inductors hate changes in current. They like to maintain current flow. And in fact, that's why in your house, if you try and unplug something from an outlet, if it has a high inductance, it doesn't like that sudden change in current from whatever it was to none. And so sometimes you'll see a spark jump from your outlet to the plug because it's trying to maintain the flow of current, and it does for just a little bit. So inductance is similar to capacitance and resistance in that it just depends on the geometric properties of the inductor. We're going to find an expression for that inductance for a typical solenoid, typical long coil of wire. We know for a solenoid that the magnetic field strength is given by this, where N is the number of loops, or number of turns, over the length of the solenoid. And since we're using capital L for inductance now, we'll use this cursive L for length. So we can find the flux through that solenoid as a result of that magnetic field. It will be the strength of the field times its cross-sectional area. So this cross-sectional area. So from above, we just put all this in for B times area. And then inductance is how much flux we're getting through the entire solenoid over the current we're putting in. So I'm dropping the 1 subscripts because now we just have one coil to look at. There's not a secondary. So I'll put in what I found in step 2 for that flux, mu naught NIA, divide by current. We see that current cancels, and we are just left with mu naught big N little n A. And having both big and little n is a little bit weird, so we're going to replace the big N, the number of loops, with, it is the, you could call it the loop density, how tightly packed they are, lowercase n, times the length of the solenoid. And where I'm getting that from is just rearranging from up here. If I put that in for capital N, I'm left with this expression for inductance. Mu naught N squared LA. And so we see that current is nowhere to be found in this expression. I see no I in it. Neither is flux. I see no B in it, no magnetic field strength. So this inductance, although it is defined in terms of those things, it's just there to relate them. It doesn't depend on them. It depends on how tightly packed the loops are, how long the solenoid is, and what its cross-sectional area is. In other words, all geometric properties. And similar to the dielectric for a capacitor, the core material, that ends up affecting this number out front, but we're not going to worry so much about that bit. Okay, so like resistance relates voltage and current, but doesn't depend on them, and like capacitance relates charge and voltage, but doesn't depend on them, inductance relates current and flux, but does not depend on them. In all cases, it's just about the geometry going on and some inherent properties of the materials you're using. And similar to we saw for capacitors, that they store electric potential energy. So this is what we saw back in the day for capacitors. Inductors store energy in the form of their magnetic fields. By opposing changes in current, they're sort of storing up energy to be able to maintain current if we suddenly have a drop in it, like the case of unplugging an outlet, or to prevent the sudden flow of current if we are reconnecting something. All right, so here is an example. They're pretty plug and chug with inductance, and that's because it is kind of a tricky concept. So we'll go through this pretty quick because it's just applying the equations directly. We want to make a solenoid with this inductance, so that's capital L, this cross-sectional area A, and this length, and again we're going to use cursive L for that. How many turns of wire are needed? We use capital N for the number of turns, and then we'll go ahead and label for part B and C how much energy. We labeled that as magnetic potential energy when we have a certain current flowing through, and what EMF is induced if that current drops to 0 in 75 milliseconds. So that's going to be our time that passes. For part A, we have information about the inductance and then the geometric properties of our solenoid. We want to find the number of turns. If I have something with inductance, this is about my only option. So let's start from there. But I want to find the number of turns of wire. That's capital N. I've got lowercase n in this. But if I remember that it is the number of turns per unit of length, I can put that in right there. If I simplify that out, I've got n squared in the numerator. I'll have L squared in the denominator, but one of those two L's will be canceled by this one. So I'll be left with just L in the denominator and then A. If I solve that for capital N, it will be multiply by the length of the solenoid, divide by mu naught A, take a square root. Inductance is 1.4 times 10 to the negative 3 henries. The length of the solenoid is 0.052 meters. U naught is 1.26 times 10 to the negative 6 Tesla meters per ampere. And cross-sectional area, 1.2 times 10 to the negative 3 square meters, we take a square root of all of that. We will get about 220 turns. All right, for part B, we're finding how much energy is stored. So magnetic potential energy, 1/2 inductance times current squared. The inductance is, again, 1.4 millihenries. The current is 2.2 amps. And so when we have that amount of current flowing through the circuit, the inductor is storing 3.4 times 10 to the negative 3 joules, 3.4 millijoules of energy. Part C, what EMF is induced? For that, it's easiest to use this rewritten form of Faraday's law in terms of inductance. So it is negative inductance, change in current over time. Again, the negative is just about Lenz's law, that this induced EMF will oppose that sudden change in current, in this case a drop. So this EMF would act to maintain current flow by pushing current through the rest of the circuit for a short time after whatever the original current source, the battery or generator, is removed. So negative 1.4 times 10 to the negative 3 henries. The change in current is final minus initial. The final value is 0. The initial is 2.2 amps. And that happens over 75 milliseconds, or 75 times 10 to the negative 3 seconds. That will be 0.04 volts. Not negative, because we get a negative from here and out front. That leaves a positive answer. So that's the size of the induced EMF. This inductor acts like a very weak battery for a short time. If you have played with the Firefly lantern at all, it's in one of the display cabinets out front, you may notice it takes a while to start up and to shut down. And that is because it has a very significant inductive behavior. It does not like the current through it to change suddenly, and so it doesn't shut off immediately like some other electronics do. All right, that is the end of chapter 22, so we will have our quiz on Wednesday. I'll see you then.